I'm going to do a couple of examples, or I'll do an example. And then if you guys, most of this week is just going to be Q&A, so I got to get the clock for the room broke, so I need to keep that on. So anyway, I'll put up a couple of examples and then take some questions. So let me get this first one up here. So you know the drill for this. Product and mechanisms. Oh, and I got to tell you something else. So if you see equivalence, that's a molar ratio. So it just says for every mole of the molecule you have on the left, you got one, for every mole on the left, you got a mole of sodium oxide. Yo, sorry.
You're good.
We're doing audio video stuff.
Is this?
And strong base.
Do you want us to draw the mechanism as well?
No, you may. You don't have to. You can if you want. I'm just asking for,
What type?
yeah, SN1, SN2, E1, E2. So yeah, the question: do you have a leaving group?
Yes.
How many leaving groups do you have? What's that?
Technically three. But like, there's one that I feel like the iodide's easiest to break off.
It is. So yeah, so iodide is a better leaving group than bromide is a better leaving group than chloride. But this one, the bromide is not a leaving group because it's on an sp2.
Yeah, I was wondering.
All right, so you can't do SN2 on an sp2 if you need a mnemonic to remember that. No SN2 on an sp2. But you can't actually do any of these four mechanisms on an sp2 carbon. So if the leaving group, so bromide is a leaving group, and you're going to get to it. There's a reaction in Orgo 2 that you'll see where that bromide could be made to react, but it doesn't here. So it is a I like saying technically it's a leaving group. Bromide is a leaving group, but it's not on a carbon that can react in these reactions. So you got a chloride and an iodide, and this is the thing about the equivalence, right? So you actually have, if I've got 1 mole of this molecule on the left, right, I have a mole of chloride and a mole of iodide. Each one of those can react with 1 sodium ethoxide. Okay, so you definitely have enough to do a reaction at both of those centers. So you got a leaving group. You have beta hydrogens.
Yeah.
Got beta hydrogens on both of them. Right, so we've got beta hydrogens here, here, and there. Okay. And so then, yeah, is this a strong base or a good nucleophile? You want to answer?
Both.
What do you? Yeah. Okay. You're just quiet. All right. Yeah. So again, like the thing you want to remember, at least with the oxygen bases, this works out pretty well. Okay, so water is a weak base, poor nucleophile. You should be able to remember that. And then what that translates to is any oxygen that's got 2 covalent bonds and is neutral is going to be a weak base and a weak nucleophile. Okay, so water is a weak base and weak nucleophile. That means an alcohol. So in this case, ethanol. Two covalent bonds, 2 lone pairs, the oxygen is neutral, so ethanol is going to be a weak base and a weak nucleophile. And the other thing to remember, hydroxide is a strong base and a strong or good nucleophile, right? So, and you should know that just from high school chemistry, general chemistry, whatever. Hydroxide is a strong base. And because any strong base that's small is going to be a good nucleophile. So then what this would suggest is any anion that's got a negatively charged oxygen that's got 1 bond to it is going to be, especially if that charge is localized, that's going to be a strong base and a good nucleophile. And so the ethoxide fits that. Right? The ethyl group is a little bigger than hydrogen, but it's on the other side of where those electrons are. So think about what that nucleophilic oxygen has to do. It has to be able to get to the carbon. So if it can kind of get stuff away, like if I needed to reach into a bin to pull something out, right, like one of those trash bins back in the back, you might say, geez, you're really big. You're not going to be able to get in there. Like I don't have to crawl all the way into there. I just have to reach my hand in there. So my hand can get to a place that the rest of me can't. Right? And that's really what happens when ethoxide acts as a nucleophile. Only those electrons out on the oxygen have to get to that carbon. The rest of the molecule doesn't have to get there. So the smaller a nucleophile is, the better it's going to be. But it can get pretty big before it gets too big. Okay, so the answer here is we do have a strong base or a good nucleophile. It's the ethoxide, not the ethanol. So you really don't have to consider the ethanol at all in the product of this reaction. Okay, and this is going to lead us to, because the answer here is yes, this reaction is either going to be SN2 or E2. So what's the next thing to consider once you get to SN2 and E2?
What kind of carbon in it? Like primaries?
Yep. What were you going to say?
Then temperature too.
Yeah. So the 2 things now are carbon and temperature. Let's do the temperature first. Temperature is low, and this would suggest SN2. The iodide's on a primary carbon, the chloride's on a tertiary carbon. All right, so tertiary carbon can't do SN2. So we have SN2 or E2. The temperature suggests E2, or sorry, SN2 is more likely, but the tertiary chloride can't do SN2. So therefore, I don't know if you guys have ever seen this, 3 dots in a triangle is therefore. This is going to be E2. Up here, primary carbons do SN2 just fine, so you get an SN2 up there. Point of this one, and I think there was one on the worksheet that was kind of like this, is you definitely should look, like, is there a leaving group should be one of the first things you ask. But you've got to, like, it doesn't mean the entire molecule has to do the same reaction. The bit that reacts is just the carbon, maybe the beta carbon, definitely the alpha carbon, and the leaving group. And so you've essentially got 3 different things to consider here. The bromide you can rule out right away because it's on an sp2 carbon. So it's not doing any of these reactions. Tertiary chloride is going to do an E2. I mean, it can't do an SN2. So if this, like if the sodium methoxide wasn't there and all you had was ethanol, you could do E1 or SN1. And the chloride could do both of those just fine. But we have a strong base, so this one's going to do E2. The primary iodide will do SN2 just fine, so the product, bromide stays there. So that should be what we get. We do no reaction on the bromide, E2 to get the chloride, or to get the alkene, and SN2 there.
I thought that you did them like all separately. That's why there's 3 equivalents. Like.
Yeah, but it's going to react, yeah. And I'm still counting the wrong. Oh, no, we get a double bond. The other thing is count your carbons. All right, so if we count, I'll come back to your question in a second. Sorry, I distracted myself. I'm still not convinced I'll get this right. 1, 2, 3, 4. Yeah, okay. I should have more faith in myself. I know this stuff all right. Right. And if you put here, I mean, the ethoxide, like I said, it's actually a fairly small base. So if you were thinking that alkene should be the Hoffman alkene, like you grab one of these. Like if this was a question on the test, I wouldn't. I'd be fine.
The reason why I was just saying, like, I did
You do 3 different,
and
yeah.
I said, like, this was SN2 and then
Right.
sites.
Okay. So yeah, you could get, the SN2 is going to be the SN2. There's no inversion or anything out there. You could get an alkene here. You could get the alkene that's drawn. You could also get this alkene with this stereochemistry switch. For that, you don't really have to draw all those. I generally, I phrase it as the major product. So if you draw the, in this case, since it's not a bulky base, if you draw the most stable alkene and that's it, I'm fine with that. But you don't have to take them, like this molecule, and I guess that's kind of what I was trying to, point I'm trying to get across. This chloride's going to react as if it's alone in this molecule. Like it doesn't, the chemistry of that alkyl chloride doesn't depend on stuff a long way away from it. Right, so if this is a benzene or a cyclohexane or a methyl, whatever, this is going to give you the same chemistry. The same with this primary carbon. It doesn't really matter, there's other stuff over here. So you can have multiple mechanisms happen on the same thing. And now, you were asking about drawing the mechanism.
Mm-hmm.
So there are 2 distinct steps. Like this is not going to happen at the same time. Right? For the E2 and the SN2 to happen at exactly the same time, this molecule would have to collide with 2 other ethoxides in exactly the right orientation. And that's just way too improbable. It's not impossible, but it's not very likely. Collisions between 2 molecules happen all the time. Collisions between 3 are pretty rare. All right, questions about that one? Yeah.
So like with the SN2 be a lot faster than the E2?
Yeah.
Okay. Would it be like,
Well, yeah, it would. I was gonna say that is a hard. We'll do a rate one next.
would it be like unreasonable to think that, at least in like some of the products, only the SN2 would happen?
No, that's probably not unreasonable because the temperature's not high. Because chloride is a much worse leaving group than iodide. So when I said that the SN2 would happen first, it's not that SN2 is faster than E2.
It's in the
Probably really E2 is a little faster because the base is grabbing a proton. There's 5 protons that could be grabbed. Whereas, you know, for the SN2, that oxygen has to hit 1 carbon. But iodide is such a good leaving group. And so, honestly, the way you would do that, like I think that would be a tough question. The rate questions you guys get on the test are going to be, there's going to be one difference, right? And this is, if you, as much as you can, I know probably none of you right now are going to grow up to be professional organic chemists. But if you're in some sort of science, actually any sort of field where you have to use logic, change as few things as possible. Right? If you want to compare, you know, you've got some, and this is why medicine, I think, there's still a lot of art to medicine because there are too many variables. Right? If we want to know, like take the vaccine, right? How does the vaccine work? What is the risk of a side effect? You're essentially running, you think, oh, we've got 100,000 people in this study. So we've got 100,000 data points. But every one of those people is chemically different. And there's a lot that humans share. So cyanide kills all of us. Like there's no one who's walking around who's immune to cyanide. But there are a lot of other drugs, and maybe you could just do this with your friends, right? Like I talk to now that we're all getting older, I talk to my friends about what do we take in the morning, right? I like ibuprofen. Ibuprofen does me really well. My wife's got to have Tylenol. I've got friends that swear by aspirin. You know, like everybody's kind of got one of those. Some people aspirin makes them really sick. Some people it has no effect. I'm going way off on a tangent here, sorry. My point is, a true scientific experiment changes one variable. And in medicine, you can't really do that, right? Because if you change patients, you've changed hundreds, if not thousands of variables. So one thing I really like about chemistry and physics, it's usually a lot easier to sort of control the system. Once you move to biology where things are alive, there's just way too much stuff going on. Like here, so the experiment you would want to do is you would because I gave you an answer. I said, yeah, the SN2 here would go faster. Mm-hmm. What we should do is we should put this molecule in an NMR solvent. So the NMR solvent would be deuterated ethanol, so it would be CD3 CD2OD. It's actually pretty expensive. All right, so now that ethanol is not showing up in your proton NMR. So we make a solution with this thing, we add our sodium methoxide, we take an NMR of the starting material, you can figure out where that signal is, you can figure out where that signal is. These two are going to be pretty distinct, that alkene is going to be really distinct. Drop in your sodium methoxide and you start watching them build in. So I try in here to give you what I think would happen. I try to, you know, when it's one thing changes, iodide changes to chloride, iodide's going to react faster. But so here you've got the leaving groups different, chloride and iodide, and the reaction mechanism is different. So you've changed 2 things. As soon as you change 2 things, it becomes a lot harder to predict. And if you change 3 things, you really, unless it's really obvious what the effects would be, it's hard to do that. Let's do a rate. should have just written this once. Okay, so first of all, do you have a strong acid or base, sorry, a strong base or good nucleophile in any of these reactions?
Yes.
Hang on. What do you think it is?
Well, you have a methyl attached to an OH, so when you separate, that's an OH. So
Will it separate?
I don't know.
That's the thing. So this is, and this is hard. Okay, so if I write that, you should see that as hydroxide, right? Because the sodium is going to be a plus. It means the O has to be a minus. And so you guys see this, and you think, oh, that's going to. So what you just said, I have seen written on many an exam. So people want to do this. But a methyl cation is the worst carbocation you can have. So really that doesn't form. And this bond is a covalent bond, not an ionic bond. Right? So just because you see an OH doesn't mean you can assume a hydroxide. That's why I asked you why you thought it was. Okay, so some people will think, oh, methanol is a strong base because it's got this oxygen. Some people will think it's a strong base because it's got hydroxide. So again, that oxygen's covalently bonded to two things. It's neutral. You don't. So the answer is you don't have, since that's the only thing, and methanol is a weak base, weak nucleophile. That's all you have. So then, what mechanism possibilities are there?
SN1.
Yeah. So SN1 or E1, the temperature is low. So if you go in here to look at the products. Here's what we get. Okay, so SN1, you don't have a strong base or a good nucleophile. Temperature's low. Going to be SN1. So now rank these. Let's say one is the fastest. 4 is the slowest. And this is probably a harder one than I would do.